This is a video to assist you in understanding how to complete the AP Classroom assignment related to Unit 7, specifically on angular momentum and torque. Number 1 has a bar with 4 forces on it. I have written the torque's direction and calculated the torque for each force. They wanted to know what is the angular momentum of the stick after 2 seconds that those forces have been applied. And if I want to know the angular momentum, then I know that the torque net times the time is equal to the change in angular momentum, which is angular momentum final, minus angular momentum initial, and the angular momentum initial is 0. So net torque, which we can calculate by adding all the torques, which is a positive 75 Newton meters. They told me 2 seconds. So 75 times 2 is 150. Number 2, I have a disk that has an initial angular velocity omega d. It's positive. I have a known rotational inertia, which is its rotational mass. They tell me it goes until it stops, and the final angular velocity was 0. Time is question mark. And they told me that we have the ability to see a single data point on here, and it rotates 100 times before coming to rest. Frictional forces are what's causing it to slow down. So what do we want? What do we need in order to determine the angular impulse that the frictional force exerts on the disk? What is the impulse? Well, in linear land, impulse is force time. That right there is impulse, and that results in a change in linear momentum. Well, the angular impulse is the torque times the time. In order to know what that angular impulse is, I need to know the change in angular momentum. The initial angular momentum, I'm sorry, the final is 0, I believe. Yeah, the final is 0. So this we know. We know the initial, which was omega d, they told us. And we were told that we know I, so we don't need any more information. We have the ability to calculate the change in angular momentum based on that. All right, same setup up there. Student must determine the angular impulse again that frictional forces exert on the disk from the moment it rotates with some velocity, angular velocity in a counterclockwise direction until it stops. Which of the following could the student have used in order to approximate? Now we need to actually calculate or measure. Again, it says approximate. You'll see why that's important. The initial angular velocity of the disk. A, put a motion sensor to collect the disk data about the disk linear position. Well, motion sensor pointed at that disk is going to send ultrasonic waves towards it. This disk is actually not moving in a linear direction, so that doesn't tell me squat. Put a motion sensor to determine something about the disk angular position. How would a motion sensor determine, here it is going around in a circle, that again, that motion sensor doesn't work that way and would not be able to tell me that. C, a slow motion camera that's able to film the disk to determine how much time it took for one spot to go around one time at the very beginning that this disk was set into motion. So again, that's approximating the initial time it takes to make one rev, and you can determine the angular velocity from that. So that's the answer. D, a stopwatch to determine the amount of time it took to go from the very beginning all the way to the very end. That would determine my angular velocity average. I would not know the initial. All right, this one's got all, I hate the way they lay this out, but anyway, I have this known I, I have the radius. I'm located at, I got 2 pieces of clay that I'm going to put on the edge at R1. And then I'm going to do it again, except this time at R2. Okay. And so now what they want to know, consider the 2 pictures. How do the angular momentum of each system, okay, L1, L2, and the angular speed of each system compare after some period of time that we've applied that force? So the force is the same and the time is the same for each system, okay? But now how does the angular momentum between each one and the final angular speed compare? Okay, well, we put a torque on each system for this. I called this system 1 here. I put a torque on system 1 for some period of time. Well, what was that torque? That torque was Fr times the radius times the time. And that's going to equal the change in angular momentum, which is the final minus the initial. They must have told us that the initial system was at 0. There we go. Okay. All right. So the torque equals the final angular momentum. How do the angular momentum of each system and the angular speed of each system compare after this time? So they want to know the final angular momentum they want to compare. Well, if I look at system 2, I apply the same force at the same distance for the same time. And so, again, it started from rest, so that will be the same value. So I've eliminated 2 answers. Whoa, come back. I've eliminated 2 answers. The L1, L2 at the end will be the same. Now, how about the angular speeds? Well, we know the final angular momentums are the same, which is equal to I times omega. We'll look at I values for each of these systems. The rotational inertia or rotational mass for I1, for the first one, has to be greater than I2 because, again, I is something related to the mass times R squared. The mass is located farther away. R value is larger. So I1 is greater than I2. If that's the case and their angular momentums are the same, then angular velocity for 1 has to be less than angular velocity of 2. So that is B. All right, we got a system, got a disk, it's got a radius R. I'm going to put a block and I'm going to drop the block that's hanging on a string, and it's going to go some distance and hit this floor. So it's going to go here and hit the floor. We know the initial velocity or angular velocity is 0. We want to know the final angular velocity. So we got to see what we have to have in order to find the final angular velocity. So if all I'm given is A, the angular displacement of the pulley and the time it takes and the time it rotates before coming to rest, because the quantities are related, the time it rotates to rest, that's not going to help me. But B and C, if I have the mass of the block and the distance it falls and the amount of time the block takes to hit the floor. So if I know how far the block goes, the time it goes, it started at rest, and I know the acceleration of the block, and that's a linear acceleration. If I know the linear acceleration, I can then use the bridge equation and find the angular acceleration if I know the radius, which is why I have to have C. So I need the radius, and then I can determine all quantities necessary to be able to calculate the final velocity. I don't need this, and I don't need this. All right, number 6. I got this graph, net torque versus time. Net torque, time, write the equations that you have that are related to that. Sorry about that. I apologize. Where was I? Ah, come on. I've already done this. Here we go. Net torque versus time. Essentially, net torque times time equals change in angular momentum. Area underneath that curve is change in angular momentum. At what time, at what instant does the disk have the greatest angular momentum? Well, area is all positive, so we're adding angular momentum everywhere. And at this point here is when the angular momentum is at its maximum, because I've added all of that angular momentum. Now the angular momentum doesn't change between that 2.2, call it 5 seconds to 2.5 seconds, because there's no torque on it. And so if you look at your answers, you don't have 2.25, but you have 2.5 seconds, and it doesn't change between 2.2 and 2.25. Okay. Number 7, same kind of graph. Well, not exactly the same. Angular acceleration versus time. Slope gives me radians per second cubed. That doesn't help me. Area gives me change in angular velocity. And they want to know how we can use a graph to determine angular momentum after 5 seconds. Angular momentum is equal to the um, uh, rotational inertia times angular velocity. This thing started at rest, so its initial angular velocity was 0. If I know the change in angular velocity, which is the area, then I know the final. And they want to know the final angular momentum after 5 seconds. So I will determine the area from 0 to 5 and multiply by the rotational inertia of the rod. So area gives me angular velocity final, since the initial was 0. I was known, multiply it by that, gets me the final angular momentum. Number 8, I got a disc that has a mass hanging on it. It's going to put a torque on that. Distance fallen. The disc falls some distance over time squared. Notice this. Look at this units here. T squared. All right. Oh, I got a straight line. Slope, meters over second squared. That's acceleration of that disk. That is the linear acceleration of that disk. Well, right there, that is going to be the acceleration tangential to that disk. And I can find alpha if I know R. AT equals R alpha. So that'll be the tangential acceleration divided by R. So what do we have? Figures 1 and 2 can be used to determine the magnitude and direction of the net torque. Net torque is equal to I times alpha. If you know the direction of alpha, you know the direction of the net torque. Magnitude and direction of the net torque? Yes, because if I have the known I value, which they told me I did. So I'm going to use the slope of the graph to determine its tangential acceleration, find the angular acceleration using bridge equations. I know I've got the magnitude of torque. So here we go, A, because we have the linear acceleration, and then we can determine the angular acceleration, and we know the net torque from that. Angular velocity versus time. Slope is radians per second squared. That gives me fishy thing. And so if I know, look at the graph, it's constant and it's negative, okay? That means torque is constant and it's going to be negative. They're in the same direction. So the student makes the comment that net torque of the rotation of the object changes direction at 5 seconds. So this is right here. Everybody wants to think it's changing directions. The net torque doesn't change directions at that moment in time. Angular velocity changes directions. The torque stays the same because acceleration is constant the entire time. So I was going forward at 50 radians per second, but I was slowing down, which means my acceleration was negative. Then I go and all the way I slow down, I slow down, I slow down until I come to a stop, but then I continue to accelerate in the negative direction. Torque never changed because acceleration never changed. So the student is incorrect because the angular acceleration is constant. Here's another graph, angular momentum versus time. Angular momentum versus time. I go and write all the equations I know that have something to do with angular momentum and time. That's the impulse equation. And so the slope of that is going to be the torque. Look at the slope, it's constant. The student makes a claim. The graph shows the magnitude, shows that the magnitude of the net torque of the rod increases as time increases. And that is incorrect because the slope is constant. That means the net torque is constant, and that is why answer C. And that is the end of this explanation video.